Yeah, so welcome to week 8 of the NPTEL Category Theory course. So, as we keep doing every week, we'll be solving problems based on the content of this particular week. So, before getting into the details of or before getting into the problems, let's first have a small recap of what is done. Yeah, so in this week, yeah, just give me some time. This will take some small amount of time. Yeah, so in this particular week, so what you learned essentially was the notion of a monad on a category, which is very closely related to the idea of monoids. So the the observation is this, that in category theory, monoids really play a very central kind of role, and many things, whatever you see, are sort of reincarnations of the notion of a monoid. So in particular, a monad is one such example. So what really was a monad on a category? It's actually the data of an endofunctor T from the category to itself. You have a natural transformation T composed T to T, which mimics composition, and you have a unit from 1C to T, which mimics the existence of an identity element under multiplication. Right, so this is the data of a monad, and this data is subject to associativity and identity axioms. Now, the interesting thing is that monads are useful in the sense that they capture algebraic theories, or to be very precise, nice algebraic theories. So, we won't get into the details of what this means, but let's just put it under caption. Captures nice algebraic theories. In other words, corresponding to every algebraic theory, you have a certain monad which sort of characterizes it. Yeah. So, associated to every monad, you also studied the concept of the Eilenberg-Moore category. Category associated to a monad. Which is essentially the category of algebras for the monad. And there was one other category that sort of probably was introduced this week, which was the notion of the Kleisli category of a monad. But I'm not really sure if that was introduced. But as far as I know, it's not examinable. But sorry. Okay. Okay. Fine, we'll just stick to Eilenberg-Moore categories, and moreover, you also have the notion of an Eilenberg-Moore adjunction associated to a monad. So essentially this is supposed to capture or answer the question. So you have seen that every adjunction generates a monad. So you ask this question whether every monad comes from an adjunction. And it, as it turns out, it indeed does. And the sort of the universal such generator is actually the Eilenberg-Moore adjunction associated to a monad. Then you studied something called the monadicity of an adjunction or of a functor. Or a functor. It's the same concept. And you also studied the notion of, how to characterize monadicity. Essentially due to Beck, John Beck, and also Barr as well. So I would just put it as Barr-Beck theorem. So roughly speaking, what it says is that a functor, or rather precisely speaking, G from some category, let's say B, to a category A is monadic if and only if firstly G has a left adjoint. So there are many different versions of the monadicity theorem. So there's a strict version, there's a crude version, there's a weak version, etc., etc. What we'll be using is this one. Everything is, the proofs are almost the same, modulo some changes. G has a left adjoint, G reflects isomorphisms, and G creates co-equalizers of pairs, of parallel pairs in B which are G split, or whose image under G has what should I say, as a split co-equalizer. Yeah, so this is roughly more or less the content that you studied this week. And before moving on to the problems, I just wanted to ask if you have any questions so far. Okay, I have a question. What does creates co-equalizers mean? I see, okay. Okay. Pranay? Yeah. 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 Yeah, so he is, he is more or less correct. So idea is you first start with a pair of arrows in B, and then look at the image. If you take any, suppose that you take a co-equalizer of the image, then there will exist a co-equalizer of the original diagram in the domain whose image is that co-equalizer. So he is more or less correct, absolutely. So yeah, so let's in fact let's not complicate. Yeah. Yes. Yes. Monadicity of a category over some category. That is what it does. Yeah. So so in a sense, what it does essentially is basically, so you might so whenever you have an adjunction, both the categories are important, right? So what monadicity does is it says that you can sort of not focus on the domain of the right adjoint, and in fact it's fully recoverable. That is what the monadicity does. Monadicity theorem does. Yeah. You have a question? Yeah. Co-equalizers in sets. Co-equal. Yes. Yeah. Yes. So basically, okay, fine. We can find this out actually. That's a good question. I don't know. Let's see. So you have set S, set T. You have two arrows U and V. You have a split co-equalizer by definition is some set C together with a function F together with an arrow in the opposite direction, right? And okay, let's not write it. Let's call it G and an arrow H. So such that what should happen? If G is 1C, then UH is 1T and VH is GF, right? Okay, so if G is 1C, what does this mean? This means that G has a left inverse, which means that G is a split monomorphism, which means that G is in particular a monomorphism, which means that G is injective, right? And hence F is surjective as well, right? So let's write down G is injective. G is a, let's write it like this. G is a section of F, right? Yeah, and moreover, you should also have Fu equal to Fv, right? So let's see, what does this mean? Similarly, H is a section of U and VH is GF. So in particular, this is supposed to be a co-equalizer, which means that C should be equal to some quotient of T by identifying US with Vs, right, for all S. So your question is what interesting or what special kind of quotient should this be? Hmm. So when I say that something, so for example, assume for the time being that these were, let's say, abelian groups, then saying something like this, that F has a section would mean that C would be a sub of, I mean, it should be a, what is that called? I mean, C should be a direct summand of T, right? Something like that. So here it should probably mean something like T should be I mean, C should not only be a quotient of T, it should also be a sub-object of T. It's a subset of T. So T should be C, I mean, co-product something, right? This is what Fg is equal to 1C means, right? Probably. Okay. So what I am claiming right now is, what am I claiming right now? I mean, there should be something more than just this. But a priori, I mean, necessarily this should hold that T should be C coproduct something. In other words, C should be a summand in the category of sets of T. But I don't really understand what to do with H. You see, U and V are already given to us. So what this is asking is H should be H should be a section, right, of U. So T should also be a subset of S at the same time. So what kind of quotient is this, which is also a subset of some object? I mean, that's essentially this kind of thing. Can you give me an example of a split co-equalizer in set? Okay. Yeah. Hmm. What do you mean by forgetful functor? You mean a faithful functor? Okay. Yeah. Yeah. Okay. So let's see. So A up to B, there is an equivalence of categories. And B to set, there is a functor which is monadic. Yeah, so what you are asking is, should this composition functor from A up to set be monadic as well? Okay, so what do you think? Let me ask you this first. It should work, okay. And why do you think so? Let's call this equivalence to be U. No, that's not, that's a bad notation. Let's call this E. Why do you think so? So, okay. So first of all, what do we need to figure out? First of all, we need to figure out that this composite functor should have a left adjoint, right? If we want to apply Beck. So how do we do that? So observe that F was monadic, so F has a left adjoint, right? Okay, so let's. Okay, my Apple Pencil battery is out. 3 minutes. Yeah, let's talk. So the point is that F has a left adjoint because F is monadic, and E is an equivalence of categories. So can we say something about F composed with E? So F has a left adjoint, and F composed with E should have a left adjoint. Why? Yes, why is that so? Yeah. Yeah. But why is there an adjunction between E and F? I mean E and H. You can say that, but actually equivalence is not stronger than adjunction. No, I understand your point, but it's not equivalence that is stronger than adjunction. I mean, something else is stronger than adjunction. It's not exactly equivalence. It's an adjoint equivalence. So the point is that every equivalence can be promoted to an adjoint equivalence, right? You can just change one of the isomorphisms. So yeah, this means that E has a left adjoint itself, and F has a left adjoint. Can we say that the composite of F and E has a left adjoint? Okay, so that's precisely the composition of the left adjoints, right? So Fe does have a left adjoint. Now F reflects isomorphisms because F is monadic, and E is an equivalence of categories. It must definitely reflect isomorphisms. So Fe should also reflect isomorphisms. So both conditions done. What about the third condition of, okay, so let's write this now. So you want to show Fe, you want to show the third condition of Beck's monadicity theorem. So take object A, take object A prime in A op, take an arrow F op, take an arrow G op. It really doesn't matter actually if you take op here. Let's just call A, just to simplify notation, let's just call A op to be, let's say, C. So take some C and take arrows C to C prime, let's say a UV in C, and assume that this FEC, FEU, sorry, FEU and FEV, FEC prime, assume that this pair has a split co-equalizer, by which therefore we mean that there is a set S together with an arrow into S together with arrows in the opposite direction. Let's not call anything. So we have something like this in set. We want to conclude that Fe creates co-equalizers, right? So how do you do that? F was monadic, so F does the job. Think about this very carefully. Apply just E. So EC, EU, EC prime, EV. This is a diagram in B, right? And its image under F has a split co-equalizer, which means by since F is monadic, this should have a co-equalizer, let's say X, C, which gets, yeah, not C, H in B, which gets mapped onto our co-equalizer, this one, or rather which is preserved. Right? Now this is a co-equalizer in B. E is an equivalence of categories. Take any quasi-inverse of E, or it really doesn't matter. If E is an equivalence of categories and if the image of this pair under E has a co-equalizer, can we not say that this original pair should also have a co-equalizer? How exactly? We can just compose with a quasi-inverse. Right? And in fact, we can also use stronger stuff like, oops, you can hear me, right? Yeah, sorry about that. Okay, I'm not getting internet on my iPad. Do you know what to do, Pranay? Oh, I got it. What was it? Yeah. 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 So E is an equivalence of categories, and the image of this diagram under E has a co-equalizer. So this diagram should also have a co-equalizer, right? Just compose with any quasi-inverse of E. Because you have a natural isomorphism, you should have a co-equalizer of this as well, right? And this will get mapped, or this will be preserved under the action of Fe. Okay, yeah, so Fe is definitely monadic. But you didn't, I mean, there was no need to employ monadicity theorem for this. You can just directly understand this just by using the definition of monadicity. So what you should have is a left adjoint, right? At the same time, the comparison functor associated to the monad generated by this adjunction should be an equivalence of categories. Since E itself is an equivalence of categories, you can actually explicitly write down the comparison functor for the adjunction between Fe, where Fe is the right adjoint, and you have the obvious left adjoint. So, I mean, there was, yeah. Okay. Okay. Yeah. Yeah. Okay. 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 I don't. Yeah. Continue. Okay. Yeah. Okay. Yeah. I mean, that could be the case. I mean, I don't, since I don't really know about these things, I can't probably appreciate the importance of this. But what I did was entirely a formal thing, right? I mean, it was just about categories, and you just take an equivalence of categories. Things are happening exactly as you should expect them to happen. So, so if stone spaces are monadic over set, great. I don't really. I plan to sometime, but I don't really know about these things. Do you have any other comments about this? Okay. Yeah, about this by split co-equalizer thing, maybe you can think something along these lines, that C should be, the co-equalizer should actually be a sub-object of T as well, and maybe you can figure something out. But I'm pretty sure that this condition is necessary. I mean, this thing is necessary. Maybe you can find, maybe it should have some specific form, etc. I'm not really sure about this now, but what we can certainly say is that whatever this equivalence relation is, that should be, I mean, whenever you factor or take a quotient of T by this equivalence relation, you should get back this block, or rather you should get C. Okay, so this equivalence relation, what should I say, the kernel of this equivalence relation should be this. Kernel makes sense, right? In any category you can just look at the kernel pair of a relation, right? So probably this, not probably, this will exactly be the kernel, as I suspect. And I don't really know what this extra conditions on H and U and V mean right now. Maybe that needs some more work. Okay, one motivation was, first of all, to obtain this monadicity theorem. So the point is that there are certain co-equalizers in general, which so for example, suppose you take any co-equalizer which is not a split co-equalizer, then I mean you cannot, what should I say, it's not an it's not an absolute co-equalizer, but so I would say so essentially this Barbach theorem was proved first by, not first, I mean it was proved in stages, and Beck sort of did the first stage of it, where he showed something. So basically you need to show that some functor is an equivalence of categories. So what Beck did was show that some functor is fully faithful if and only if something happens to be a regular epimorphism in some category, very crudely speaking. And the idea that he used was this notion of a split co-equalizer to do that, because it turns out in many cases that this whenever you take a monad T on a category C, this forgetful functor ut from Ct to C, actually, it turns out that certain things in C are split co-equalizers. Image of some parallel pair in Ct under Ut is a split co-equalizer in C, but it's not a split co-equalizer in Ct, but it turns out to be a co-equalizer, or it turns out that it has a co-equalizer. Okay, so roughly speaking, what I can say about this motivating this is probably this came from Beck's original theorem, not the monadicity theorem, something before that, which sort of characterizes fully faithful functors in terms of, fully faithful right adjoints rather, in terms of the co-unit of an adjunction, which turns out to be a co-equalizer, but whose image turns out to be a split co-equalizer. Yeah, I don't really know anything else about this. Maybe if something comes to my mind, I'll tell you in due course. See, these are just, of course they are important conditions, but of course no one will say that a split co-equalizer is more important than a co-equalizer. So it's, split co-equalizers just makes life easier, maybe. There is something that I kind of have in mind, but let me formulate something and tell you. Okay, any other questions for now? Okay. Yeah, so we'll start solving problems for this week, and Yeah, we'll only solve 3 problems because that will only take a lot of time. So let's start with a very simple one, a basic one. So you know what a well-powered category is. Everyone here knows what a well-powered category is. The class of subobjects of any object is a set. Right. So basically what you do is you take an object C in a category. You can look at its subobjects. A subobject is defined as an equivalence class of monomorphisms into C. And if you look at the class of all subobjects of the object C, then this should be a set, not a proper class. If this happens for every object C, then the category C is said to be well powered. Okay, so let C be a well powered category and let T be a monad on C. Then you need to prove that C power T is well powered as well. The Eilenberg Moore category is also well powered as well. What can we do? Start with an object XH in C power T. Okay. What does a subobject of this mean? So let's say AG is a subobject of XH. So what does this mean? Yes. Okay. Oh, I thought this was settled that X, the first component denotes the object and the second component denotes the struct. Yes. Okay, so what this means is you have TA, you have TX, you have A, you have X, you have F, you have TF, you have G, you have H. This commutes in C. F is a monomorphism, but in CT, right? We don't know if it is a monomorphism in C. Yeah. So can we say that F is a monomorphism in C as well? Okay, okay, cool. So suppose A to X you have F. Where should I take the morphisms to be? Yeah, I mean, okay, so tell me tell me 2 morphisms. PQ, let's say. No. Monomorphisms are left cancelable, right? So let's say some object P, Q. Yeah. So assume that FP is FQ. Okay. Yes. Yes, this is the claim that F will also be a monomorphism in C. Yeah. Okay. 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 T dot. Okay. I don't really know if this would give you something, but I mean, there's a easier way of claiming this. That is what. So observe that, for example, let's say a submodule of a ring. I mean, a submodule of a module is in particular a subset of the underlying set of the module, right? So something like this is happening. A yes, is a subset of the underlying set of the module, right? In particular. Similarly, let's say an action of a group on a set, if you take a sub action, that is again a subset of the underlying set. So something like that is what we are claiming here. That is, if a comma g is a subobject of xh, then the underlying object of a comma g, which is a, will also be a subobject of x. So I'll leave this as an exercise for you to figure out, for everyone to figure out. So from c power t to c, you have a functor u, the forgetful functor. Do we know anything special about this functor? In general, for any monad T, do we know anything special about the functor U? It's faithful, it reflects isomorphisms, okay, but it does it has some more property, right? Which is that it's a right adjoint, right? So it's a right adjoint, and you are taking a monomorphism in C power T. So will the image of that monomorphism under U not be a monomorphism again in C? Since F is a monomorphism, in C power T, UF is a monomorphism. In C, UF equal to F, let's say, yeah. Is this okay? Yeah. So F is a monomorphism in C power T implies UF has to be, because right adjoints preserve limits. That's the idea, right? So UF is equal to F is a monomorphism in C. So which means that X is a subobject. A is a subobject of X, right? So what we essentially have is associated to every subobject AG of XH, we have obtained a subobject A of X, right? So what we have is essentially a map, or rather we can say that U restricts. Okay, so let's write it properly. So we have a sub-object A of x. So U restricts to a, oh, by the way, the motivation behind, I'm sure we know this, but the motivation behind saying that UF will also be a monomorphism is something like this, that you can think of monomorphisms as being characterized by kernels, right? For example, this is just an example. I mean, we can give a finer argument of this as well, but think of it as monomorphisms are given by kernels. This is sort of algebra week going on. So think of monomorphisms as given by zero kernels, and kernels are equalizers, right adjoints preserve equalizers, etc., etc. Same line of argument follows in general, roughly speaking. Okay, so U restricts to a what? U restricts to a functor from sub, let's say CT x comma h to sub C x, right? What does this do? It sends the equivalence class of some arrow, some object, some arrow to the class of A. I should also mention the arrow F here, but it's understood, right? U restricts to a functor like this, which is defined on objects in this way. We don't need to worry here about the morphisms, because all we want to prove is that this is a set. Okay, now what can we say? Oh, by the way, we haven't proved something, then we can claim that U restricts to a functor. We need to prove that it's well defined, right? So tell me, if A comma G and A prime comma G prime are equivalent as sub-objects, does that mean that A and A prime should also be equivalent? So if A, so let's say, take A comma G to F, F to XH, and take A prime G prime to F prime XH, right? Assume that F and F prime, A comma G and A prime comma G prime are equivalent, that is F and F prime factor through each other. We'll just write it in words. Does that not mean that UF and UF prime also factor through each other? Yeah, hence UF, and because U is a functor, that's all. In C. So U restricts to a functor in this way. Now it's well defined, at least on objects. It's automatically well defined on morphisms as well. So we have this, let's say, map at the level of sub-objects. So let's write it like this: OB sub CT. Oh, okay, I don't know, but I think I've lost my mind today. Why am I writing functor? Because we haven't even claimed anything about sub CX being a category. So let's say the object part of U restricts to a function, to a map from sub CT XH to sub CX, sending the equivalence class of AG to the equivalence class of A. This is well defined as proved, hence a function. So let's what do we need to show? We know since C was well powered, we know sub CX is a set. What can we show now to claim that sub CT XH is also a set? Or something's No, if it's onto, then it's possible, right? That subcity XH could be larger. We want to show that the domain is, we want to put restrictions on the size of the domain, right? So what should we have? We know that the codomain is small. Yes, injection. We claim that this function is actually an injection. So what do we do? Claim what we need to show that. What do we need to show that? Okay. Yes. AG and let's say AG A prime G prime together with so we have arrows. I mean, it's understood that we have arrows from A comma G to, okay, this is, we have arrows from A comma G to XH. So take sub objects, and we have an arrow A prime comma G prime to XH. Yeah, now let's say this is F, this is F prime. What do we need to show to claim that the function is an injection? We have taken two sub objects and we assume that okay, or we could assume that their images under the above function are equal. That is, and assume that, I mean, it's the same contrapositive just, and assume that class of A is equal to class of A prime. In C. We need to show that class of AG should be equal to class of A prime G prime in C power T, right? That's all. So what does it mean to say that class of A is equal to class of A prime in C? Keep in mind that how did we obtain the class of A? So A, the object A together with the same arrow F, right? So we showed that this arrow is a monomorphism even in C. This is how we defined our function, right? So this class of this is equal to class of this monomorphism. I mean, we have abused notation a bit. We should really say class of a monomorphism, not the domain of a monomorphism. Yeah, so class of F is class of F prime. Okay. I mean, I hope that it's, I don't really like writing inappropriate notations, but let's say F, right? A comma F, A prime comma F prime. Yeah. Yeah, class of A prime, I mean F prime X. Assume that this happens in C. What does this mean? This means that so as sub-objects of X, F and F prime are equivalent, which means that what does this mean? Okay, and not only so, they are isomorphic, making a certain diagram commute, making the obvious triangle commute, right? So there exists an isomorphism A to A prime, let's say H, making this commute F prime. Yeah, this happens, right? Now what do you think? We want to show that the original F and F prime, I mean this subobject and this subobject are equivalent. So we need to show that F and F, I mean there is an isomorphism from A comma G to A prime comma G prime in CT, making that triangle commute, right? So what isomorphism? Okay, so we'll come. Okay, we'll come to that. But what isomorphism should we choose? So we want to have an isomorphism here, making this commute. What isomorphism should we take? We already have this in C. You mean H, right? You mean H, right? Okay, so let's see this. So we have H from A to A prime making this commute, and H is an isomorphism, right? So we claim, so to show that F and F prime are equivalent in C power T, this would mean that we want, so we want an isomorphism from what to what, A comma G to eta, I mean A prime G prime, XH, this is F, this is F prime, such that this commutes. Everything in CT now. I want an isomorphism here. What is a map in the Eilenberg-Moore category of algebras for a monad? It's just a map of the underlying objects which is compatible with the structure maps, right? So which means that what I really need first of all is a map from A to A prime, and since the forgetful functor from CT to C reflects isomorphisms, what we want really is an isomorphism A to A prime, a priori, which satisfies compatibility with G and G prime. Now, do we already have a candidate for an isomorphism from A to A prime? H. So what we claim, or what should the claim right now be, is H from A comma G, or this is a bad notation again, H from A to A prime is actually a morphism H from A comma G to A prime comma G prime in CT. This is in C. This is what the claim should be, right? So what we need to do for that is show that this diagram commutes TA prime, A prime, H, TH, G prime. We want to show that this diagram commutes in C. So want to show that this diagram commutes in C. Then we are done, right? I mean, not exactly done. We have just produced an isomorphism, and that will be enough to show that that this commutes. I mean, this triangle commutes because this triangle commutes in C. Yeah. So how do we show that this happens? How do we show that G prime compose TH is equal to H compose G? H is something very arbitrary, but H has this property that H makes this triangle in C commute. How do we use this information to show that this diagram commutes? So this is like one of the informal ideas in category theory, where to show something, what you essentially do is apply everything that you have. This is an informal principle. So what is because so the idea is that everything is so natural in category theory that suppose you start with two different approaches to something which are natural enough, roughly speaking, then they are bound to give you the same result in a certain sense. Or uh, I mean, corresponding to an input of a particular type, doesn't matter what this type means, put that in quotes. Corresponding to any input of a particular type, you will have exactly one output of another type. So best is to use everything that you have at hand, and you should get a result. So the point is that what I'm trying to stress here is that we haven't really used the fact that H makes this triangle commute. How do we make this fit into this diagram? We can just put f and f prime here as well, right? Okay, let's put question mark here. Okay, let's not write it like this. So we have this diagram. Let's extend it by using all the information that we know about H. H is an isomorphism which makes this commute. Can we say something now that the upper square should also commute? We don't know if the entire diagram commutes. We don't really know if this upper square commutes. We want to show that the upper square commutes. How do you show this? Any ideas? Yes. You are on the right track. So Hg is equal to G prime TH. No. I mean, there is, but I mean, you know, right, that if we took F to be an arrow in the category of T algebras from AG to XH. So going from TA to A and then to X is the same as going from TA to, okay, let's use a different color just so that we don't get confused. Going from TA to TX and then to X. This is H, this is TF. This commutes, right? And going from TA prime to A prime to F prime is the same as going from TA prime to TX prime to, to TX to X. Again, you have H here and you have TF prime here. This commutes. So we want to prove this. And you said that we have to use F prime H is equal to F. So why not just, why not? What is T? Oh, T, capital T. I mean, that would only complicate stuff, right? I mean, why would you apply T here? We want to use this fact, F prime H is equal to F. So just apply compose with, just post compose with F prime on both sides. Let's see what happens. So observe, what is F prime composed H composed G? What is this? So let's this, right? So this, since the triangle commutes, we can write this path as this, right? Since this the left hand square commutes, I can write this as this, right? Since, okay, so now what to do? H compose TF. Okay, okay, okay. So let's write it. So F prime composed H composed G is F composed G, which I can write as H composed TF, right? Now what can I do? See, I want to show that, so I don't really know if this is correct. What I am trying to show here is if I compose with F prime on both sides, I should have this F prime compose, oops, F prime compose G prime compose TH. I want to show that this holds. Okay. So I should have on the other end F prime compose G prime compose TH. What I have so far is, from this I have obtained H compose TF. So how do you show? I mean, what do you do next? What do you do next? Yes, yes. So what do you do? Sorry, what did you say? H compose TF is? So you are saying this H composed TF is H composed with TF dash composed with TH. Why is that? Why is that the case? Okay. No, but why is this equal to this? I mean, what tells you that this equal to this? So we already know F prime composed H is F, right? So applying T on both sides, TF prime composed TH is TF, right? So yeah. So this is not really the way that one would prefer to argue in category theory, because what you want to do is draw diagrams for everything and not write equations. Equations are things in algebra, and the correct analogs in category theory are commutative diagrams. So, but just to make things simpler today for us, we'll just write everything in equation form. So F is equal to F prime composed H implies that TF is equal to TF prime composed TH. This we have. So as you said, H composed TF is H composed TF prime composed TH. Now what is H composed with TF prime? This is equal to? Yeah. So this is F dash composed with G dash composed with TH, right? So see what we wanted. Okay, why are we done? No, okay, we wanted, we are done with that, and in fact we are done with the problem. Why is that? So we have this already. No, F dash was something very specific, and F dash has this property, right? Which is, as you can see from the barbed tail of the arrow, F prime is a monomorphism. So it's left cancelable. Since f prime is a mono, we have G prime compose TH is equal to H compose G. And hence, let's put a label on this diagram 1. So diagram 1 commutes, right? That means, so H from A comma G to A prime comma G prime is a morphism in C power T. Since H from A to A prime is an iso in C, hence H from A comma G to A prime comma G prime is an iso. Why is this the case? So you start with a morphism in C power T, category of T algebras. Look at its image under the forgetful functor. The image arrow is an isomorphism actually. So why does that mean that the original arrow that you started with is an isomorphism? Isomorphism, exactly. So think of something like, this is analogous to statements like what we learned in basic algebra. For example, group homomorphism is an isomorphism if and only if it is bijective, something along the lines of that. So what essentially is the content of that statement is that an inverse which exists since the map is bijective should also be a morphism, which is exactly what this is saying, right? So yeah, so this is an iso in C power T, and finally, because U is faithful, since A prime H X F prime commutes in C, hence so does A comma G, okay, A comma G, A prime comma G prime, H F X comma H, okay, what the hell, okay, I used a bad notation, let's call it T because H is already used. T. So let's say T. T. Okay, sorry. TT. So T. T. T T T T T T. I'm sorry about this. Okay, I fully messed up the notation right now. Okay, I'll write this later, but yeah, the problem is solved. That we can agree. Okay, I'll finish this up later. It's just time consuming. Okay, any questions so far? Okay. So for the next two problems, which are the last two problems, what we'll be doing is we'll be using a notation which I am writing here. So what we do is, for a functor f from a to b and any category C, we have a functor from C comma A, the functor category from C to A, to C comma B, the functor category from C to B. What it does is essentially post composing with f. So sends a functor h, which is a functor from C to A, to the functor fh, which is from C to B, does the same to h prime, and sends a natural transformation alpha to the Godemont product f alpha, or the Viscott composite f alpha, right? So diagrammatically speaking, what we have is this: CA h prime alpha is being sent to C to B fh prime f alpha. Everyone is okay with all notations here, right? And what the functor is doing. Okay, so f star is will denote this functor by f star, or you can also think of it, or write it as f compose dash. That is what it is doing essentially. So let's keep this notation in mind, and let's start with a monad T on a category A. So these are straightforward exercises, only require some labor, that's all. So start with a monad T on a category A, and let C be a category, arbitrary. What we claim is that T star has a monad structure. So T star, which is from C comma A to C comma A, is an endofunctor of C comma A. This has a monad structure itself. Pretty straightforward. Just tell me what the structure is. You can verify the axioms. I mean, this is for all the viewers. You can verify the axioms yourself. We'll just write down the essential stuff. Yeah. So T star is our functor from C comma A to C comma A. What does it do? It sends any H to T composed H. What we want is a mu from T star composed T star to T star. And what else do we want? Okay, so we have already used mu. Let's use mu hat, and eta hat from what to what? To T star. Yeah. So question is, how do you define mu hat? What's the most natural thing that you can think of? So these are functors from C comma A to C comma A. Defining a natural transformation is just defining the components of the natural transformation. So take any object in C comma A, let's say H. What should we define mu hat H as? So mu hat H should be from T star of H to, since these are functors, I am writing a fat arrow here for the component as well. Yes. T is an endofunctor with a monad structure. Yes. So we want a natural transformation from T star H to T star H. What does T star do? Just post composition with T. So this is exactly this is exactly T composed H. And this is exactly T composed H. What should you take? Yes, mu H. And by the way, mu H notation is clear to everyone. I'm repeating this again. Mu H is just mu star H, or what it does is I mean its component at some object, let's say dot, this natural transformations component at some object dot is exactly mu at h dot. This is what the natural transformation is. And what else do we want? We want an eta. Yeah, okay, so let's write for all h in c comma a. You can check. In fact, there's nothing to check actually. Is there some? Yes, there is something to check. So check that mu hat is a natural transformation. Nothing to check here, that this is a natural transformation, understood. This should be an arrow here, so it should be a natural transformation. This is understood because we already know that mu h is a natural transformation. What you need to check is mu hat is a natural transformation. In other words, this mu hat at h is natural in the variable h. So mu hat is a natural transformation. And how do we define eta hat? Okay, so eta hat at h should be from h to t star of h, which is t composed h. So what is eta hat h? Eta h. So I define it as eta h. Again check that eta hat at h is natural in the variable h. So check that eta hat satisfies naturality. Okay, so these are natural transformations. Very good. Verify. What else do you need to verify? We won't do this. You can just verify this on your own to the readers. I mean to the viewers. What do we need to verify? First of all, the associativity and unitality, making t star mu hat eta hat a monad on C comma A, right? Okay, these questions have more insight to them, by the way. I mean, these are not just stray problems that I have put up. Okay, let's not confuse people. Yeah, so let's start with B. So the Eilenberg-Moore category of T lower star, which is in fact this one is more interesting. So the Eilenberg-Moore category of T lower star has been shown to be a monad, or has been shown to have a monad structure. We can formulate its Eilenberg-Moore category of T star algebras. What you want to show is this is isomorphic to C comma AT. Not only just isomorphic, naturally isomorphic actually, but let's just focus on isomorphic. Okay, so let's yes, isomorphic as categories, not just isomorphic, naturally isomorphic, and in fact something more as well. But for now we just focus on isomorphism of categories, isomorphic as categories. Okay, so T star, recall, is a monad on CA. Exactly. So we can consider T star, consider the Eilenberg-Moore category CA power T star. We also have one, so let's keep it here. And let's write this here. What we want is an isomorphism from this to that of categories. So what are the ways that you can think of at least obtaining a functor in the first place? Okay, write down the objects. That's, I mean, define the functor explicitly. Done. What else do we know? Do you know anything about the universal property of the Eilenberg-Moore category of a monad? I mean, that's again a very strict term, but do you know any special property of the Eilenberg-Moore category of a monad? Okay, which category? Okay, okay. So, what can we say now? So, if it's terminal in the category of adjunctions, and by the way, what is that functor which does the job, which makes it terminal? For every adjunction that you have, you should have a functor from the domain of the right adjoint to this Eilenberg-Moore category of the monad generated by that adjunction. So, what is this functor called? That's the comparison functor. So what I'm claiming is this functor should be a comparison functor for some adjunction. What adjunction can we take that actually induces this comparison functor? So whatever that adjunction is, this is understood that this should be the right domain of the right adjoint, right? And whatever that adjunction is, that adjunction should generate the monad T star. Okay. The domain category, yeah. Oh, yeah, there is a natural functor, right? You can think of here. We'll come to that. We'll come to the explicit formulation of the functor. But let's focus on the adjunction. Okay, so let me do this in two different ways. Actually, we won't write much, but so let's say a priori want a functor from c comma a power t to c comma a power t star. Wow. So what functor should we have, right? So first, I mean, what is this called? Approach. One approach is to use that this is the Eilenberg-Moore category of T star. So consider, we fully know that what adjunction should we take. The adjunction, the domain of the right adjoint should be this, and the codomain of the right adjoint, or rather the domain of the left adjoint, should be C comma A, right? So that the monad generated is T star again, and you have a functor from this to this. So consider the adjunction, the usual adjunction, the one which is given to us already, but which we already know about, a power t, the free forgetful adjunction, right? So what does your intuition say? If I apply, so this is a functor. I mean, so ft and ut are functors, right? And I can take c comma a, I can take c comma at, I can take ft star, and I can take ut star, right? What does intuition say right now? Okay, but before that, what does intuition say? Wait, there should be an adjunction here as well, right? Why? Why should there be an adjunction here as well? So ft star is, so claim is not claim, there is an induced adjunction. There is an induced adjunction this one. Why is there an induced adjunction? So what is ft star doing? Ft star is composition with ft. What is ut star doing? Post composition with ut, right? So to have an adjunction would mean that if you fix an h here, take an arbitrary h here and take an arbitrary k here, then arrows from f, since ft star is supposed to be the left adjoint, arrows from ft composed h to k in c comma a power t are the same as arrows from h to ut composed k, right? Is this correct? Yeah. And why is this the case? What is an arrow? What is the content of a natural transformation from ft composed h to k? It's exactly a class of arrows, a family of arrows from ft of ha to ka for every one for every a in C, and then the content of some natural transformation here is an is a family of arrows from h is ha, right? Yeah, ha to ut of ka for every one for every a in C. Since ft and ut were adjoint in the first place, with ft being the left adjoint and ut being the right adjoint, there is already a correspondence, a bijection between arrows of this form and arrows of this form, right? Right? Understood, right? Yeah. So you have an adjunction. Alternately, you can use the triangle identities. Yeah. So there is an induced adjunction. Right. And what is the monad generated by this adjunction? The monad, or check, I should say check, because I'm not writing things in detail. So check that the monad generated by this adjunction should be T star, because at least for the functor part, what is the monad? What is the functor part of the monad generated? That is ut star composed ft star, which is exactly ut composed ft composed with something. This is your functor, which means it is t composed with something, which means that it is T star. So by this adjunction is T star, and you can check the multiplication and the unit. So so you have a functor, a comparison functor. Right. And we can in fact directly write down the definition of the comparison functor using, since we know what comparison functors look like, but let's write this directly without using this approach. So alternate approach. So we want a functor, a direct approach. We want a functor from c comma a power t to c comma a power t star. right? What functor should we take? An object here, so let's call this functor to be omega, very bad notation. An object here is a functor h from c to a power t. What we want really is a functor, is an object in this Eilenberg-Moore category, which essentially consists of some functor c to a. An object looks like this, together with some, let's call this functor, for the time being let's just call this f, together with some natural transformation from t star f to f, right? Okay, yeah. So what at least for the functor part, what can we say? What functor from c to a can we use? So let's write it properly. H is a functor from c to a power t. We want a functor from c to a. What functor can we have? Can we get a functor from c to a? Think of the I mean, if you would like, you can also recall the construction of the comparison functor and understand what this comparison functor here was doing. Then, I mean, this omega that we are defining is just the comparison functor itself, except that we are taking a direct approach. Yeah, what do you think? Or you can use some property of the comparison functor. It makes two diagrams commute, right? So you can use that as well. So c to a power t you have h. Do we have something from a power t to a? Yeah. So we have something from c to a. Okay, so let's write this properly. So this omega functor takes an object which is a functor from c to a power t h, sends this object to this c to a power t h. I'll try to put simpler problems in the sense that less laborious problems from next week. ut, the forgetful functor, right? So you can just, okay, let's write ut composed h, c to a ut composed h, and you should have a natural transformation from t star of ut composed h to what? This is Eilenberg-Moore category. You should, what should the structure arrow be from what to what? The structure arrow is from t star of ut composed h to ut composed h. Yeah, what natural transformation can we take here? So what does t star do? It's just post composing with t, right? So t star of ut composed h can be written as t composed ut composed h. We want something from this to ut composed h. This is a bit tricky, but not that tricky. Again, you can just recall the construction of the comparison functor, write everything down, or you can do, we are taking a direct approach. So what is a natural transformation from t composed ut composed h to ut composed h? So since ut is involved, I mean, we know that ut is the forgetful functor from at to a, and t is involved. Why not, let's just write everything in most simplest terms possible. So in other words, this is right adjoint to ft. Let's bring ft into the picture. What is t? T is just UT composed FT, right? So let's write this as UT FT UT H. So from this to UTH we want something. Now what? No, why do we have that? FT was our what was the first problem? I also forgot. Yeah, putting a monad structure on T upper, T lower star. That's a different thing. So let's write it then. So a power T, you have FT, you have UT. What I want is a natural transformation UTFT UTH to UTH. What can we use? Sorry? Okay, how? Correct. Yeah, so epsilon T, epsilon power T, let's say, is from FTUT to identity on A power T. This is the, yeah, this exists, this we know, the co-unit of that junction. So how do we use it to obtain a natural transformation on the right? So UT and yeah, UT epsilon T and H. Yeah. So let's just write this as UT epsilon T H. Right? Done? So check that this is a functor. This is again a Laborious task. That is what was sort of curved by our previous approach. So check that omega is a functor. And what else do we need? So yeah, by which in particular I also mean find out the action of omega on morphisms. What else do we need? We need an inverse functor for this functor. So we also want, because we want to prove that omega is an isomorphism, also want a functor from C comma A power T star to C comma A power T. What functor can we take? Let's write an object here. It's C to A H, let's say, together with, okay, C to A K, together with an arrow T star K to K alpha. We want to obtain a functor from C to A power T. Let's say this functor is K comma alpha hat. Just a bad notation. Or let's say this functor is F power K comma alpha, let's say, associated to the pair K comma alpha. So this is a functor. This should send some C to some object of A power T. What object should we take? This should send any object C to some object of A power T. What, yeah. Take KC, which is an object in A, fully agreed, and we should have a map from TKC to KC. So alpha C. check that this is a functor, and in fact it's direct, or you can directly check that these two functors are inverses of each other. So let's call this functor to be omega. Okay, let's call this functor like this. Very, I don't know what this is. Yeah, check that is a functor and are inverses, and that does the job. In fact, everything was defined naturally. There was no arbitrary choices involved here in any definition, right? Which means that this omega should also be the component of some natural transformation, which depends naturally on A and naturally on C and also on T. So this is isomorphic to C comma A power T. Okay. So interesting thing is, basically whenever you take this C comma gap, this is a functor, right, from cat to cat. What this is saying is, so this is like a representable functor, right, from cat to cat. Functor which is rather co-represented by C. So what this second result is actually saying is that this co-representable functor preserves Eilenberg-Moore categories of monads, right? Agree? Right? What do we know about representable functors in general? No, that's for all functors, right? What do we know about in terms of limits, co-limits, can we say something about a representable functor? So for example, yeah. What can we say? Yes. Representables preserve limits, right? Here we have a representable which preserves an Eilenberg-Moore category, right? And what is an Eilenberg? This is a very rough intuition. This is not exact, but what is an Eilenberg-Moore category entirely given by? So you start with the category A and you describe some equations, some restrictions on your category, rather some equations which allows you to define A power T, right? Which means that Eilenberg-Moore category is like a limit, right, of some data. Agree? Because you can think like like an equalizer, you can say. Those things are not being, I don't want to get into the precise details of that, but the idea is A power T is behaves like a limit, right? Whenever you put restrictions on something, think of it like an equalizer. Saying that two things agree means that two maps are being equalized by some inclusion, etc. Right? So A power T is like a limit, right? It's like a limit, right? So what this result is actually saying here as well is that this representable functor sort of preserves, I'll put this under quotes, the limit, because this is not precise. So in some sense, what this result says is that it does this. Okay. So sort of restores back your faith on co-representable functors preserving limits. Okay. Yeah, we'll get into the next problem. We will again just write short details about it. But before that, let me ask you something. So I understand that the Kleisli category is not examinable, but I just want to know how exactly was it defined in the lectures. So, and what is the universal property? So suppose T is a monad on a category C. How do you define the Kleisli category CT of the monad? Objects are same as C, okay. 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 This is exactly a morphism A to TB in C. Right. Okay. And do we know any universal property? I mean, was that covered, the universal property? Okay. Then I think if he has introduced Kleisli category, I'm pretty sure he will also introduce the universal property. It's the initial object in the category of adjunctions. Okay. And we can also directly obtain the Kleisli category in terms of the functor ft, right? Just look at the full subcategory consisting of the free algebras. That and C lower T are equivalent. So you can also think of the Kleisli category as that category, right? So those two are equivalent. You can either look at the full subcategory of the Eilenberg-Moore category consisting of free T algebras, or you can look at this abstract category whose objects are the same as the objects of C, and whose arrows from A to B are exactly arrows from A to TB in C. Right, an arrow in this direction in CT is exactly an arrow A to TB in C. Okay, that's your Kleisli category. Any questions so far? Okay. So last problem, show that a functor, we'll do this quickly, show that a functor G from B to A is monadic if and only if G star in our previous notation from C comma B to C comma A is monadic for every category C. 1 second, just a second. Are you leaving? কেন আমার হয়ে যাবে এক্ষুনি 8টায় শেষ হয়ে যাবে, জাস্ট ওয়েট ফর 10 মিনিটস।
করতে পারি ওকে, আরে ওই একটা ছেলে খাবে বলে গেস্টটা বন্ধ করে দেয় আর কি।
ও আচ্ছা, তাহলে চলে যাবে। ও চলে আসুন, ঠিক আছে,
সরি।
হ্যাঁ, ইটস ওকে, টাটা। Sorry, yeah. We have our previous notation G lower star from C comma B to C comma A. So we want to show that a functor G from B to A is monadic if and only if G star from C comma B to C comma A is monadic for every category C. Quite a powerful, it's not a result actually, a problem, but a powerful statement actually. Yeah. What do you think? Let's try to show the forward direction. Yeah. Okay, so G from B to A. So suppose G from B to A is monadic. Okay, so G has a left adjoint. Yes, of course. But we want to apply monadicity theorem, right? So we want to in particular obtain a left adjoint for G lower star. So we already know what F star is, right? So yeah, so the point is that since you have an adjunction if G, this induces an adjunction C comma A, C comma B, F star G star, right? So G star has a left adjoint. What else do we need to show? Okay, so why does G star create co-equalizers of pairs which are whose image under G star is split? So G star is from C comma B to C comma A. Yeah. Why does G star create co-equalizers for G star split pairs? So take H, take K, take two arrows alpha beta. Assume that, so take a parallel pair. Assume G star of H, G star of alpha, G star of beta, G star of K is a has a split co-equalizer. Now what? So let's write this data. G star of H is G composed H. You have G star of alpha is just G alpha. You have G composed K. You have G beta. This has a split co-equalizer. Let's say T, some functor T. This has a split co-equalizer. The interesting thing about, yeah, sorry. Okay, but what would that do? Yeah, so we have that there is a split co-equalizer, right? Yeah, so what we want to show is that G star creates a co-equalizer. That's all that we want, right? What we want is this should have a, this original diagram should have a co-equalizer, right? So we know that this is a split co-equalizer. The interesting thing about split co-equalizers is that they are absolute co-limits. So what can we say? So in particular, we can say that G composed H of some object A to G alpha at A, G beta at A, G composed Ka to Ta, this is a split co-equalizer, right? This co-equalizer is splitting for each object A. C, right? Agree? Yeah, so now what can we say? Since G was monadic, since G is monadic, the original functor G that we had is monadic. So what can we say now? HA to KA, alpha A, beta A has a co-equalizer preserved by G. Finally, what can we say? So it has a co-equalizer. Let's say the co-equalizer is some arrow TA, some let's write it properly, some arrow TA, some object VA, which depends on A. So what can we say? What? Yeah. Yeah. Yeah, that needs to be checked, right? Yeah. So check that. Since everything is defined in terms of co-equalizers, universal property, universal object, and universal, co-limits, universal objects, or in fact co-limits in functor categories are computed object wise. So this is, you don't need to check it, but still check that V from C to B, sending A to V is functorial. I'll just put this in star star because this is really something that you need not check, because everything is defined in terms of co-equalizer. You always have maps induced. Is functorial, and T, which is defined to be this class TA of arrows from K to VA, A in C. Is this correct? A in C? Yeah. Is what? Is a natural transformation. K to V, and T is the co-equalizer of alpha and beta, and G lower star preserves it, because G preserves it object wise, so G lower star will preserve it. These are just facts, that straightforward facts that need some straightforward checking, and hence you are done. You should also show, that is again, it depends on the definitions that you are taking. There are various different ways of defining creation of limits, co-limits, etc., etc. That's all confusing. You should also check that this G lower star reflects isomorphisms, which it definitely does, because G does it, and everything is done object wise. So also check reflex isomorphisms as isos are given object wise. And G reflex isos, conservative. Okay, so by Beck's monadicity theorem, by Beck's theorem or Bar-Beck theorem, G star has, is monadic. How do you show the converse? So now you are given that G star from C comma B to C comma A is monadic for every category C. How do you show that G from B to A is monadic? Okay. Okay. What should we do? Okay. So if you take, I'm sorry, my ears are paining. If you take C to be equal to B, will that do something? Because that is just the the category of endo functors on B, right? So tell me, so this is, let's go with our intuition right now. We want to prove this direction. So assume that for every category C, our functor G lower star from C comma B to C comma A is monadic. What we want is G is monadic. Now let's go with our intuition. So for example, the category of sets has a very nice, interesting property that it is a concrete category, right? You can talk about elements of a set. How exactly are elements of a set detected? Maps from singleton, the terminal object to a set S are exactly the elements of S. In other words, what you have is a natural isomorphism from star comma gap to identity on set, right? In other words, the category of sets is representably concrete. Star, in fact, is this functor is faithful, so you can understand star is a separator, right? So what I'm saying is there something similar? So let's ask this question. So this is for sets. Do we have some object in the category of groups which can detect elements of groups? Because groups, the category of groups is also concrete. Do we have some object such that maps from that object to a, yeah, sorry, yes. So maps from this object to a group G are exactly elements of G. No, because you have only one map in that case. It's Z, right? The group of integers. Maps from Z to G are exactly elements of G. In fact, for any category of R modules, maps from R to M are exactly elements of M. So R represents the identity functor on the category of R modules. Z represents the identity functor on the category of Z modules. Right. So my question is very simple right now. Something along these lines. Is there a category which can, such that functors out of that category can detect the content of an arbitrary category? So suppose what I want, and exactly. So you take this category, there is only one object and only one morphism, which is obviously the identity arrow. So this functor category is exactly isomorphic to the category B. Why? Because a functor from this category to B is exactly, and just chooses an object B0. Let's say B of B. And what is a natural transformation from F to G? This is exactly a map from the object chosen by B to the object chosen by G. Right? Exactly. Because the domain category has only one identity arrow and nothing else. So naturality is trivial here. Right? You don't need to check naturality. Right? In other words, natural transformations or the components of a natural transformation, in this case there is only one, because there is only one object in the domain, are purely unrestricted, because a domain category doesn't have any arrows. So this actually capture maps. So this functor category is actually isomorphic to B. So now what we have is G lower star from this comma B to this. Again, this is a natural isomorphism, by the way. This comma A. Okay, I'm sorry. We are almost done. I don't know why is this happening today. I can finish it by speaking, yeah. But then again, I have to write it later. Okay, I'll finish that later. I'll just say that, yeah, so what was I saying? Yeah, just a minute. Yeah, exactly. So C is now one object and one morphism, and this isomorphism is natural in the category B, which means that the functor G lower star is exactly the functor G for the case C is equal to one object and one arrow. Now G lower star is monadic exactly means therefore G is monadic, and you are done. Okay. Yeah, I mean, I cannot connect from my iPad right now. So, yeah, maybe we will stop the session this week. Do you have any questions? No. Okay, I'll stop the recording. Okay.